I'm working on the PHORWater project, and the consortium, it includes DAM. We are specialized in wastewater treatment management. We are working on several wastewater treatment plants, mainly in Spain, but some other also in other countries like Italy. And we're also working in this project with Calagua Research Group from University of Valencia, and they're specialized in wastewater treatment research, with LAGEB, which is the Automation and Process Engineering Laboratory from Lyon 1 University. And they are specialized in crystallization, well, actually in crystallization processes, reactors design. And so they've been in charge of our design. And well, the project is been taking place with a live contribution from the European Commission. The main objective of PHORWater is to demonstrate at pre-industrial scale the availability and sustainability of the correct management of phosphorus in a wastewater treatment plant, obtaining estuarite by crystallization. What we do is we suggest a way to recover limited resources phosphorus from wastewater treatment plant, avoiding the environmental problems from phosphorus discharges to water bodies, and trying to go towards circular economy of phosphorus. The technical part of PHORWater, it's divided in these 5 actions. We first did an integral management of the wastewater treatment plant. Then we design, build, and start up the crystallization reactor. We implemented it in the wastewater treatment plant. We've done validation of we've studied the obtained estuarite. We've done analysis of the product obtained. And we have done agricultural application assays. So I'm going to start with the first one, integral management of the wastewater treatment plant for phosphorus recovery. We didn't consider phosphorus recovery as something apart from the wastewater treatment, like all the process. We think since phosphorus arrives with the influent flows to the wastewater treatment plant, and it has to be removed if we don't want it to go to the water bodies. The only way that we have to remove it is through the sludge. So we have to include this management in the phosphorus recovery in this whole management. Well, discharges to water bodies should be limited in order to avoid eutrophication problems. And it can be done either by dosing aluminum or iron salts, or by enhanced biological phosphorus processes. If we do it by dosing aluminum or iron salts, the problem is that the phosphorus will still go to the sludge, but it will not be in an easy bioavailable form. It will be in the sludge, but it won't be very useful for the plants. So what we do is improving the enhanced biological phosphorus removal. But then we have the problem that after the biological treatment, we have an anaerobic digestion. And when you combine anaerobic digestion with biological phosphorus removal, then you have the problem of uncontrolled precipitation of estuarite in the pipes. And these are the effects that that you can observe. So that was the reason to start on working on this project. In PHORWater, we have moved from less to more. We started improving the biological phosphorus removal process. Then we went to a whole study of the sludge flows, and we did simulations in order to determine which was the best configuration to enhance the phosphorus release. And finally, we implemented the crystallization reactor. The project is taking place in Calahorra Wastewater Treatment Plant, which is in La Rioja, Spain. Well, that's the capacity, and it's an H2O wastewater treatment plant. As I mentioned before, it has anaerobic digestion, and it has phosphorus removal, so it's the best example for uncontrolled precipitation. We started the project with the characterization of the water and sludge lines. At the beginning, we found that, well, those were all the points that we were studying. And we found that the average removal in the water line, it was around 80%, which is quite good efficiency. And then we were studying the sludge line. And through the sludge line, we found the lower, well, those in blue are the phosphorus concentrations in those flows. And what we found is that after the anaerobic digestion, there's a drop in the phosphorus levels. And that's indicating that some phosphorus losses is taking place right there. So we think that if we want to recover as much phosphorus as we can, we should do it before those losses are taking place. We found that the highest phosphorus availability was in the mixing chamber. The main loose phosphorus point was the anaerobic digestion. And with this configuration, before we started doing anything, just studying all the flows, 14% of the phosphorus entering the sludge line was available for its recovery. Then we use the SAS, which is a software tool developed by University of Valencia. And with this simulation tool, we were considering different strategies in order to improve the phosphorus release along the sludge line. The results of this study showed that the elutration of the mixed sludge in the gravity thickener was the optimal configuration. So that's what we did. But we had to consider three main points. Those were the elutration flow, the digestion flow, and the sludge height. Those were the limitants in our wastewater treatment plant, because we didn't improve anything until here. We were using the mixing chamber from the wastewater treatment plant, and we were using the gravity thickener that it was already built in the wastewater treatment plant. So these things were the main flows and the main characteristics that we had to keep in mind. If we increase the elutration flow, of course, we're going to increase the phosphorus release, but then the sludge blanket height in the gravity thickener will go up, and we will have problems with the overflow from the gravity thickener. So those were the main steps to control. As a result of this configuration, the average phosphorus removal in the water line was improved from 80% to 92%. And the phosphorus loss in the anaerobic digestion, of course, was reduced because we were removing it before. And what we found is that we could double the amount of phosphorus entering the sludge line, so we could double the amount of phosphorus available for its recovery. Well, after all these studies of the configuration, we started with the design, build, and start up of the recovery plant. The first step that we took, it was do it in a smaller scale, in a lab scale. We had a small crystallization tank, and we used the real thickener supernatant, the real gravity thickener supernatant from the Calahorra wastewater treatment plant, and we tried to crystallize STOWA in the laboratory. The lab scale reactor that we use, it's the one in the picture, and it has a mixing zone, and it also has a settling zone. The mixing zone is where STOWA precipitates, and the settling zone is where it separates from the liquid. The hydraulic retention time in the mixing zone has been decreased from 4.4 to 1. And the obtained results show that in any case, efficiency was always above 95%. But what we can see in this chart is that as we decrease the hydraulic retention time, we also reduce the recovery efficiency. And that's actually something like logical because of the dynamics. Like the settling, it's going to be worse if we increase the flow. So that was like expected. So we finally decided to design, well, not a lab scale, but not a full scale, a reactor. It's been designed for 20 cubic meters per day with a hydraulic retention time of 2.5 hours. And this reactor is an stir mixing, it's a complete stir mixing tank with the settling zone on the top. Computational dynamic simulations have been performed to determine the position of the inlet pipes, to determine the position of the stirrer in the reactor, which was the optimal, and to ensure that dispersion of the 3 inlet flows were efficient. It was also important to evaluate the supersaturation reached near the injectors, and actually this is all the main steps in the design were the flow dynamic simulations. Since pH conditions are very critical to obtain S2I, well, this is our reactor, we also develop a fuzzy control to ensure that the pH in the reactor was the optimal for S2I precipitation. And we started up the reactor, and these were our startup conditions. We started up the reactor with 4 hours, almost 4 hours of retention time, with a pH of 8.7. And the phosphorus concentration coming into the reactor, it was 92 milligrams per liter of phosphorus. And at the beginning, we got an efficiency, precipitation efficiency of 88%. The recovery efficiency wasn't too high because it was at the beginning of the project. Well, with this solution, our S2I production was around 9.5 kilograms per day from only 20 cubic meters per day of incoming flow. Well, our next step is the implementation of the recovery phosphorus demonstration plant, and we've been following the results. Since July 2015, the recovery reactor has been working continuously. And during this period, we've been monitoring the reactants consumption, the energy consumption, and the S2I recovery. The startup conditions at the beginning of the project, we started with molar ratio magnesium to phosphorus from 1.6, and the hydraulic retention time was around 4 hours. With those conditions, we got an efficiency of almost 92%, and we were obtaining at the wastewater treatment plant almost 8 kilograms of S2I per day. We're still working on that. Then winter arrived, and enhanced biological phosphorus removal went a little worse. So the incoming flow, it wasn't that good. We only got like around 7 milligrams per liter of phosphorus incoming. But even with that lower concentration, we still got an efficiency of over 90%. And the most important thing is that we reduce the molar radius, so the magnesium chloride consumption. We reduce it to like in a half, because at the beginning of the project, the ratio was 1:6. And at this moment, we're working in a ratio between 1:3, 1:2. We're getting it lower right now. And still, the precipitation efficiency, it's around 90%. Sorry, I just went backwards instead of forwards. And during this period, we have also observed, well, we've been monitoring the whole wastewater treatment plant results, and we have observed a reduction in the sludge production of 13%. And that's good because we have less sludge to move, to treat. But also, as we reduce the sludge, and we have also reduced the polyelectrolyte ratio, we have reduced the polyelectrolyte consumption. So actually, that's one benefit that we have found with the implementation of this recovery plant. And it's been only with 20 cubic meters per day reactor. We're not treating the whole, like as much as we could. With this plant, we are recovering the 2% of the phosphates coming into the wastewater treatment plant. And if we try to, I mean, if we could do this in a bigger reactor, this value would go up to 17% of the phosphorus incoming the wastewater treatment plant, if we could treat all the overflow from the gravity thickener. Well, finally, we're getting to the validation of the STOWA obtained, and finally we'll go through the agricultural application assays. The crystals obtained at the wastewater treatment plant has been characterized, and we have analyzed the phosphorus, magnesium, and calcium content. And also we have considered the organic carbon content. And we've done several analyses. We have evaluated the size of our product, and it's always about above 200 micrometers. So we think it's like quite good for a marketable product, quite good for fertilizers producers, and also for the agricultural application assays that we have done. They could apply this product just directly on the soil. And we've done X-ray diffraction analysis, and this show that the obtained product is most of it STOWA, and if there's another fraction, it should be less than 1%. The energy dispersive X-ray spectroscopy showed that the obtained product is 12% phosphorus, almost 10% magnesium, and 5.5% of calcium. And the atomic absorption spectroscopy shows that metal content in the obtained STOWA is lower than in any other product recovered from wastewater treatment plants. We have also gone over priority substances, and we found all of them above the limit of detection. And well, I think we could say that our product is like good quality STOWA from these results. And we're finally getting to the agricultural application assays that are still taking place right now. We've done 2 different assays on potato and on wheat crops. And each assay, it's like, it has 3 different parts. The first, well, different treatments. The first treatment, it's been only with the STOWA that we have obtained in the wastewater treatment plant. The second one consisted on a mix between STOWA and commercial fertilizers to improve our fertilizer with the other nutrients that S2I doesn't have. And the third one was only with commercial fertilizers. Well, these are pictures of the application size. And, well, the crop's growth has been monitored during all this time. And, well, these are the potatoes that we just got, and we didn't get the weeds yet. And nowadays, what we're doing is that we are evaluating the crop's yield, the leaves, soil, and product analysis and characteristics in order to evaluate the security of the S2I application as fertilizer. We don't have these results yet. The assays potato assays should be finished at the end of June. And wheat assays will be finished along July. So we will probably have these results available in our website, like maybe along August, before September. So our expected results are just right here. And we did get, we reduced the sludge production. Well, I didn't talk about the energy demand because we haven't like quantified yet. We haven't done all those analyses yet, but what we have observed with the wastewater treatment plant data is that by improving the crystallization reactor, the energy consumption, it hasn't go up. So we think that, I mean, we're using energy for the reactor, of course, but we think that maybe the nitrogen that is not going back to the influent through the through the flows. I think that could be a reason to don't observe an increase in the energy consumption. Also, it's in a small pilot plant, so we don't know if maybe with a bigger one we would observe any increase or decrease in the energy consumption. And that's all. Thank you very much.
Are there any questions? Everything clear? No, of course not. Good. Thank you, Cora.
In the Netherlands, we did also some experiments with production of struvite, and well, if you look at the granules over here, they are very nice, the crystal clear granules. And what I learned from the other experiments with struvite crystals is that they are very difficult to handle in agricultural machines. So you have to process them before you can use them. Is that also one of the things you're taking into account when you want to well, sell it as a fertilizer or whatever?
Yeah, actually, as I mentioned, we are more thinking on providing fertilizer industry than using it just directly on soil. First of all, because struvite has phosphorus, has magnesium, but it doesn't have other nutrients that also plants need. And also because maybe combine it with other products, the phosphorus bioavailability from the struvite could be increased. So, I mean, struvite is a slow release fertilizer, and maybe that's a problem, like depending on the step of the crop, on the step of it could be a problem because the amount of phosphorus that the plant needs to grow, like the phosphorus demand could be higher than the struvite solubility. So maybe mix it with some other compounds. We could improve this in struvite. And that's why we're more focused on fertilizer industry than in like agriculture just directly.
More questions?
Thank you. Karel de Waal, Neurisis. The story that the struvite has to have a certain dimension is a gospel that is put into your heads by certain priests. Our struvite that we work together with a fertilizer company is actually grinded to powder to mix it with other compounds to make a new product. So actually, I don't think that size matters.
Thank you for your comment. Other comments? Reactions? No? So what about your organic fraction in your struvite? There's no organics in it? Or?
Yeah, there is some organic, but it's very, very low.
Okay, so
as
that's
I mentioned,
not
it's less than, I mean, the purity that we have observed, it's over 99%, so we have less than 1% of organic matter, so it is not a problem.
That's not a problem for the fertilizing industry either.
Well, they didn't say that. They didn't mention, and they were interested by this time. I don't know what, I mean, we just, we have some contacts, but we are not working yet on that. So I don't know, maybe further they find that it is a problem, but right now it is not.
Okay, good, then keep it as not. Other questions? No, then I would like to raise, oh, yes. Then I'm not raising a question.
I'm hesitating because I'm by far no biochemical engineer or whatever. But what strikes me, as far as I understand, is that you put the struvite reactor in a different place than the other solutions. Because you said I put it before the anaerobic digestion.
Well,
and is that something is that a key principle of your idea, or because what's the innovative part of it? Is that point, or?
Okay, what we try to do is first of all, we work in wastewater treatment plants. So our problem was the uncontrolled precipitation. In order to avoid the uncontrolled precipitation, if we improve the crystallization reactor after the anaerobic digestion, we didn't get that problem solved. We still have that problem. So we thought that if we could improve the phosphorus release before the anaerobic digestion, we could avoid any problem after that. So that's why we thought about doing an elutration, like doing a small anaerobic digestion, a very quick anaerobic digestion before the anaerobic digestion in order to keep the sludge in anaerobic conditions so phosphorus would be released. And that's what we do. So it is not that we thought that everyone, no, it's that as wastewater treatment operators, our problem was after the anaerobic digestion, so we wanted to solve it before. We are also thinking about improving in our project, adding the dewatering water, the dewatering flows, adding them to the crystallizer, because that would probably improve the efficiency. But our main problem is that our crystallizer is small. So I don't know if we will get to do it, or it will just be something that we will do later on.
Okay, thank you very much.